We'll be looking at entropy today. We have seen Clausius theorem. Clausius theorem states that cyclic integral of delta Q by T for any reversible cycle is equal to 0. So, as it is shown here, this box. Okay. This is valid for any reversible cycle. So whatever the reversible cycle, we will any arbitrary process. We have a PV diagram. Can be any process. So long as it is reversible, you can apply this thing and get cyclic integral of delta Q by T is 0. This is going from A to B and so on. Okay, so we'll prove that this is related to entropy, and this is a property of a system later, a bit later. Okay, so we know that such a function which does not depend on the path. So in a general case, the heat transfer delta Q is a function of path. It's a path function. It is different for various processes. For example, it is different for an isobaric process. It is different for isothermal process. It is different for isochoric process. For various processes, the equation is different. So, but here, if we take it in a cyclic integral in a path, so delta Q by T, for a reversible cycle, this is 0. So we can consider this to be something like a property of a system, as it only depends on the point that we choose. So even if I choose a point here, when it completes a loop, the change in that property is 0. So change in that property is 0. So it only depends on that particular point. It does not depend on the path. Hence, it is a point function. So we assume that the point function, or we give a letter S to that point function, and we represent that function as, we call that function as entropy. Okay. So as I've shown here, cyclic integral of delta Q by T for a reversible process, R represents the reversible process, is equal to cyclic integral of ds is equal to 0, where S is the entropy. So S or entropy is a extensive property, as it depends on the mass of the system. So we can specify in case of specific quantity, it is smallest, that is specific entropy. In case of the molar quantity, it is S bar. Okay, so for a unit mole. So if we remove the cyclic integral and look at a single process, if we consider a process going from process A to process B, we can write this as integral from A to B delta Q by T, or for a reversible process equal to integral A to B ds. So this is equal to SB minus SA. As I was mentioned, as this is a point function, it will not depend on the path. It will depend only on the endpoints, the start and end point of that particular process. So this is represented by delta S. Okay, in the differential form, if we remove this integral, we will get the differential form. We will get integral. We will get delta Q by T for reversible process equal to ds. So all these equations are valid equations for entropy. Okay. So we have seen the equation for, or what ds is, the mathematical definition for what entropy is. So we'll be looking into the significance. We'll be looking into the significance of entropy after it. So in general, delta Q, or we know that heat is defined as an energy in transfer that occurs due to a temperature gradient. So if I have T1 and if I have T2, and if T2 is less than T1, heat will flow. So delta Q, I'll just represent delta Q. And delta Q, the heat will flow due to this temperature gradient of T2 minus T1. So heat is generally a function of temperature, or in particular temperature gradient. But here we say that we have perceived that for any reversible process it is not the case. For any reversible process, this fraction or this ratio delta Q by T for any reversible process is a function of its ends function. It's a function of its endpoints. Okay. So and we look into a definition of entropy. What entropy is? So entropy, just referenced it from textbook. So entropy is defined as a thermodynamic property that provides a quantitative measure of disorder of a given thermodynamic state. Okay, so by a classical, this is a classical definition of entropy. That is, entropy is a measure of disorder of a system. So true to its nature, entropy measures the disorder of a thermodynamic state. So entropy, the things that we have to know is entropy is a mathematical parameter which is defined theoretically and with a huge practical significance. So entropy cannot be measured directly like measurement of temperature, pressure, or volume. You can't have probes directly measure because temperature, pressure, and volume are physical parameters. Entropy is a theoretical construct. But one of the most significant aspects of entropy is entropy along with other parameters. So we'll be looking into what these other parameters are. Provide a quantitative measure of the directionality of a process. So this is very significant. So entropy will give an idea of the spontaneity of a process. Entropy with other parameters will give an idea of the spontaneity of a process, or if we give some heat, or if we exert some work on it, it will give us a directionality on which direction the process will go. Okay. Next, we'll look at a very simple proof that is proving that entropy is a state function. That is, we have already seen this. Like we already know that entropy is a state function because it only relies on its endpoints. So we are just putting a mathematical construct on it. So what we do is we consider two systems or a single system in state 1 and state 2. I will just represent the system Z. So the state, suppose these are gases. So the state 1 is pressure 1, T1 and S1, and state 2 is pressure 2, pressure 2, temperature 2, and S2. S represents the entropy. So we have three processes, all are reversible. Process A takes a system from state 2 to state 1, and process B and C takes a system from state 1 to state 2. Okay. So this is represented in this PV diagram here. All are the same. Okay. So here we can construct two cycles. Okay. Cycle 1 would be cycle CA, and another cycle is cycle BA. Okay, both of them are cycles, reversible cycles, because in each component processes are reversible processes. We have assumed so. So by just doing a mathematical analysis, a formal mathematical analysis of what we had defined as entropy of the processes that we have just seen, So first is cycle CA. In case of cycle CA, we have a cyclic integral of delta K by T of CA, which is a reversible cycle, is equal to 0. If we expand the cycle, it composes of cycle C, in which heat is being added, and in case of cycle A, heat is being rejected. Okay. So in this cycle, I'm going from cycle, in case of CA, I'm going from this point to this point via this path, and returning to the initial point via this path. Okay, so this is positive and this is negative. So yeah, the negative sign represents, again, negative sign represents that the heat is being rejected. Okay, so bringing this to the other side, I'll get integral of delta Q by T r is equal to integral over the path A minus delta Q by T. Both are reversible. Okay. And we can do the exact same thing with the cyclic BA, and I'll arrive at almost the same equation. So I'll combine these two. We'll combine these two. So if we combine these two, we'll get positive. It's positive. If we combine these two, we'll get integral over the cycle, integral over the path B, delta Q by T is equal to this thing, integral over A minus delta Q by T, which is a common factor, and integral over C delta Q by T. Okay, all are reversible processes. So we can, if we expand this, we'll get delta as 1 to 2, or as the process goes from 1 to 2, this is delta as 2 to 1. The process is going from state 2 to state 1, and delta is 1 to 2. Okay, so just expand it. If I expand it, we'll get S2 minus S1 is equal to minus of S1 minus S2 is equal to S2 minus S1. So we can say that delta S remains the same, that is S2 minus S1. So whatever path we take, if we go from state 1 to state 2, the change in entropy for a reversible process is always represented by S2 minus S1. It does not matter what path we take. Hence, this is the classical definition for a point function. So we say that entropy is a point function. Okay.